Hello, everyone, and we are welcomed to today's lecture. We will be continuing with slabs. So I think just a recap of what we looked at the last time. We generally focused on, I think, uh, conventional slabs, or what we call solid slabs, all right? And we did mention that there are slabs that do in terms of the load transfer, I think we're focused on the load transfer or the load distribution. And then we mentioned that a slab is like it's like a panel. So it has a longer side or a shorter side, or at least it has two dimensions with respect to the cross-sectional um, area or the plan, let's say the plan area. Okay, so the plan area and depending on the ratio between the longer and then the shorter side, the load distribution um, can either be what we call a one-way load distribution or a two-way. All right. So with the one-way, the loads are typically transferred to the longer beams. All right. And then we came up with the analysis and then the design process for for slabs which are spanning in one direction or one-way slabs. And with the one-way slabs, we have two types, either simply supported slabs or continuous slabs, all right? And with the simply supported slabs, they behave almost the same as that of beams, all right? The only difference with simply supported slabs, one-way or one-way continuous slabs has to do with the width that we use, all right? Normally with beams will have varying width, maybe B is 300 millimeters or 250 or some other value. But with slabs, because they are panels, we take a meter width of the slab, all right? So normally for slabs, the B in most of our calculations is going to be 1,000 millimeters or 1 meter. So that is a key difference between the beams and then the slabs. All right. So I think we looked at one key component, which has to be the span to effective depth ratio. Because of how thin slabs can be in terms of their thicknesses, they can easily be susceptible to deflections. All right. So we would want to ensure that whatever thickness or height that we choose for our slabs, they are adequate to prevent any deflections or any excessive deflections from occurring. Right. So we went through the process of being able to calculate all of that. So again, we saw how to go through that process. So that's from the last lecture. We also looked at how to design one-way spanning solid slabs, right? So with the one-way, we have two options, one that is simply supported and then one that is continuous over a number of supports, all right? So, so this is the example we went through that. I'm just trying to recap what we looked at so that going through this, I mean, then the next subtopic will not be something and entirely new to us, right? So the few things you look at, so we look at in design, we look at basically or for the ultimate limit stage design, we focus on the bending and then the shear. All right. We could also focus on the buckling, but usually we assume that the members are restrained against some form of lateral torsional buckling. All right. So basically, we focus on shear and then we focus also on bending. So we check the bending strength of the slab and also check the shear strength of the slab. Right. Then from there, we also normally would have to look at a serviceability limit state, and normally has to do with deflection checks here and there. But that is where the span to effective depth ratio comes into play to ensure that our slabs thicknesses meet minimum span ratios so that the deflection failure does not occur. So we did that for both simply supported and also for continuous slabs, all in one direction, right? So some equations, some coefficients are needed to be able to analyze and then design such slabs. Okay. So for today, or for today's lecture, we will be looking at so we'll still be focusing on slabs. So let me put here slab design. But this case, we will be looking at slabs spanning in two directions. So with that, we'll still end up with either a simply supported or we can still have continuous slabs. All right. All right. So now let's look at this. Let's try to define these two. I mean, what we mean by two directions or two-way. All right. So typically, if you have, let's say this is a panel, I'm just going to use that to explain that. Let's say we have these distances. Let's say this is your Ly, this is your Lx. Okay, just using variables, all right? So if you find a ratio of the longer span, so let me say longer span, all right? Um, Normally, we assume that Ly is a longer span by convention, all right? Then the Lx is the shorter span. So if the ratio of this is less than or equal to 2, we assume that our slab is spanning in two directions, all right? Um, oops, why do I have this? Okay, so if it's less than or equal to 2, then our slab is spanning in two directions. And what it simply means is that normally or conventionally, you would have, oops, that's too thick. So you would have beams. So these are beams. Let me use a different color for the one here. Not you. Let's go for green. So we have beams, let's see at the ends. All right. So let me call this beam 1. This is beam 2, beam 3, and then we have beam 4. So these are the 4 beams that are at the periphery of the of the slab. All right. So this is a slab or a panel. And what this means is that the loads coming from the slab will be distributed to um, all four beams. All right. And the distribution of the beams is or what portion of the slab loads get transferred to the beams is dependent on the arrangements of the, or sorry, it depends on the length of the spans. I mean the Lx and then the Ly, right? So why do we prefer, or why are we going through this process? Why are we trying to learn? I'll I'll talk more about the load distribution soon. Why do we need this? All right. Normally in design, we would come to realize that slabs are typically, all right, are typically supported on all sides. All right. Or let's say in this case, the four sides, since we're looking at four sides. So let's put four sides in the bracket. And so because of that, it is economical that we design, or should I say more economical? So it is more economical uh, to design slabs on this basis. All right. The fact that they usually would span or they have supporting on all four sides and also effectively spanning in two directions. So now let's and basically I mentioned I think slabs are basically plate-like structures, right? They are quite like in terms of their thicknesses is very small as compared to the um as compared to their plant area. All right. So so let me put over here slabs are plate-like structures. Okay. So because of that, we need to look at how to what's the word? How to design such plate-like structures. And again, because of that nature, they'll be bending in both directions. All right. So they'll be bending in both directions. So bending occurs in both directions. We'll explain this again shortly. And the bending, or should I say, the amount of bending is dependent on a number of factors. All right, so let me just put that in a different color. The amount of bending is dependent on dependent. Um, so two things. One is the support conditions. All right, so the support conditions play a role. We'll look at what they are. Then basically the ratio of the two spans. So this is what determines the kind of bending that we have. All right. When it comes to the ratio of the two spans, all right. Um, so you can have a case whereby let me rather draw. Um, where's my mouse? Okay, go back. Let me see if I can get this thing working. Okay, my screen just decided to go off again. Oh no, it didn't go off. Okay, I just messed it up. Just give me a second. Let me see what I can do with this malfunctioning screen. Uh, ever since I updated to Windows 11, I think I just have to go back to my Windows 10. Okay. So let me share the screen again. Hopefully this time around, everything works. All right, so I think we are back in business. Yeah, I'm still recording. Great. Okay. So let's say we have these tools, but I wanted to draw some shapes, and that's what landed me in all this trouble. Okay, so let me just draw some nice shapes. Yeah, I want to make this one, and then make this one another shape. Need another shape. Okay, let's go with this other one. Okay, so these are two different shapes. All right. The first shape, we could say that this is our ly. This is our lx. All right. So the first shape, our lx is equal to ly. All right. So basically, the ratio will be the ratio of ly over lx will be equal to 1. Okay. So basically, this is supposed to be a square. Okay. So when it is a square, loads are distributed equally to all the supports. Okay. To all the supports. That's something to take note of. If so, for example, if I have these supports, so I'm going to draw the supports with red. That's not the best way to draw them, but it's fine. So just to show that we have all these supports at the ends. Okay. So if I'm distributing my load, this is how the load distribution would work like. Oops. Okay. So I have some load going to the beam here, and that load going to that beam, and that load going to this beam, and that load going to that beam. Okay. So we have the same proportion of load in terms of how much load that goes to the beam. Right? And this is typically a triangular load. We've all come across triangular loads before. All right. So this is a triangular load. Then here, so here we have, let me just use the black. Okay. So this is our ly, and here we have our lx. So ly, lx is more than 1. So let me see in this case, it's more than 1, but then it's also uh, less than 2, less than or equal to 2. Let's put it into this frame so that it still falls within the fact that it is spanning in 2 directions. Okay. So again, we have we have this, we have that. Right. So the load transfer would have, oops, no, let me use it out here. Load transfer will have a shape like this. So the shorter spans or the spans which are of shorter length would receive triangular loads, and then the longer spans will receive trapezoidal loads. So let me put that into writing. Let me see if I can do some bit of division. Okay, let's go. So that at least we know that they are, this one looks more like K, but this one, okay, it's not K. So this is like rectangular in shape. Okay. So let's say shorter span beams have triangular loads. Uh, all right. And then the longer spans, longer span beams, you have the trapezoidal or trapezium loads. I mean, same thing. Okay. All right. So that's the load transfer. Let me just add the arrows to show where the loads are going to. All right. And definitely the loads are going to affect the moment that you calculate. All right. And the moment definitely moves with the bending, right? So again, depending on what the spans are, the loads can be distributed differently. All right. Um, the other thing has to do, so this is for lesson. Let me call this one maybe. So this I. So basically what I've talked about is I. And for the I, which has to do with which has to do with the support conditions. Let me just put over here support conditions again. What this simply means is that just like in the case of when we had um, where we have what's the name? Where we have beams, sorry, slabs that were spanning, whether they were simply supported or continuous. We also have the same thing with two-way spanning slabs. All right. So with the support conditions, we can have what we call continuous support or continuous over supports, and then there's continuous over supports. Okay. What these simply mean is that with a continuous over support, there are moments. So there's a moment at supports, moment at supports. Pretty much that's what it means. While this continuous support, it means that the moment at supports is zero. All right. So moment at supports is zero. Oh, this is not equal to zero, or this is zero. That's how we look at it. Okay. So for example, uh, what it simply means is that uh, how do I define? Okay, let me just use this. We had the panel system from our first lecture, I think our lecture. I'll just bring that up quickly, and then we can look at how that's going to help us. Bring that over here, paste that quickly. Okay, great. So here we have this, right, from our first lecture, right? Now, if you look at, so I'm going to label the panels nicely so that at least we know which panels we are dealing with. So I'm going to call this P1, P2, this is P3, then we have P4, P5, P6, P7, and then P8. All right. So here we have a void. So this is a void, right? Or it's an open space. All right. Now, if we look at okay, and I'll need to draw one more, but it's fine. Let me just see. If I can extend these lines, it's gonna be. Oh yeah, I can. Interesting. Okay, just extend these lines a little bit, just so that it helps me to achieve my aim. Might not be as perfect as it's supposed to be, but we will take it like that. All right. Mhm. So basically, what I'm showing you here are beams. All right, nothing more, nothing less. So I think I'm going to move this down here since it's black, which was so indicates the what's the name? The supposed to indicate the slab outline. All right. So just have to create another one here. All right, so this is what we have. All right. I'm going to move the void from where it is and bring it in a new place so that it helps me achieve what I want. So there's a void. Okay. So now this will no longer be P. So now here becomes P8, P9, P10, and then P11. Great. Now I want to explain this whole what's the name? Continuous spans and all of that so that we appreciate what is happening. So the length, so this is LY2, this is LY3, LY4, then we have the LX and L. Please take a note, take note that the LY and the LX is not really about the position of the slab. It's more has to do with which panel, if you pick any particular panel, which length or which span is longer, which span is shorter. All right. So it could be your LX is always the shorter span and your LY is always a longer span, regardless of the orientation of your panel or your slab panel. Okay. So now if you look at P1, P2, P3, let's assume that let me use this to color code those guys here, just to explain some concepts. Okay. So I think this is here. So when it's yellow, at this support, at this support, we have a pin support. Right, so this is a pin support. Right, then here, the beam is acting as a fixed support. Then let's look at the ones over here, the ones on this side, which is always the one that is difficult to, unless you shade, which is fine. So let's just make these ones right. So this is also fixed supports for now. Maybe this is fixed. I should have just changed the color. What should I do? Okay. Let me change the color for one. Then hopefully it works. That was gonna be. Let me just erase. Okay. Okay. Erasing is oops. Erasing is not always easy. Okay, great. Okay. Let me also make this one yellow. Okay, I'll come back to why I'm making it yellow. I mean, we can just play around with it just to explain the concept, so it's fine. So we know that anytime we see a yellow, it means that it is what simply supported. Let's make this one. I need something. I need something to work with. Okay, that's fine. I'll come back and play. Let me do something again. Let me raise the side. Sorry. Okay, it's fine. I'll be moving around, so it's fine. Let me make this one also yellow. Okay. So let me say that instead of P5, instead of P4 and P2, I have a void. So I have a void over here, another void, and so I have voids on these two. So this is a void, this is also a void. Okay, I'll be changing them. So now if I take P1, if I take panel P1 and I draw panel P1, what this means is that, so this is my panel P1. Okay. P1 here, this side is simply supported. Brown color. This side is simply supported, right, by the fact that we have the yellow over there. This also simply supported. All right. And because there's a void, so let me call this void 1, void 2, void 3. Because of void 1, it means that on the right of the panel, this beam over here, right, doesn't have a panel or doesn't have a slab on the right. So the beam at that point is also a simply supported beam. All right. So here you also have a simply supported beam. Let me just say simple support, simple support. All right. Then again, when you come to the side, also you have, again, because there's a void 2, it means that there's, on this end, there'll also be a simple support. Okay. So because of this simply means that your slab P1 is discontinuous on all sides. All the different support at those ends are acting as simply support. All right. So anytime a support at a slab or at the end of a slab, which normally is going to be a beam, right? Because we are dealing with solid slabs, which is a beam slab conventional design. So that's the support at the slab, if it doesn't have any adjoining slab, right, on the other side of it, or where you are not explicitly stating that the beam is a fixed support, then the assumption is that those beams are simple supports, or they are the pin support for the slab. All right. So this slab would be what you call two-way simply supported slab. So that's what we mean by continue. So this is also we can say that this slab is discontinuous on all sides. Okay, because all sides are simply supported. All right. So if it is simply supported, or if the support is a simple support, whether it is a pin or a ruler, then that is discontinuous. If the support is an internal support or a fixed support, then that becomes a continuous support. So maybe, so let me state it here. So for discontinuous, so, so for a discontinuous over a support, then the end support is either a hinge or a ruler. All right. And then if it's a continuous support, then this also means that the end supports um, are fixed, okay? Or yeah, so them just say they are fixed, right? Okay. It's easier that way without complicating matters. All right. So we will look at a few things, and I will look at how to analyze panels. All right. So before we look at the analysis of the simply supported two-way slabs, There are a few notes that I want us to have in mind, which is critical to whatever we are going to be doing. And the notes are so we have one, the moment that we're calculating, so moment in each direction. So basically we have to look at moments in each direction. A span. So where it is a two-way or one-way, this notes apply to them more, right? Sorry, that's a two-way. If it's simply supported or continuous panels for two-way, these notes apply to the two of them, all right? So moments in each direction of span are generally calculated using coefficients. Okay, so that's what makes this a bit easy to do. Okay, and this coefficient can be found, what's the name? So the coefficient can be tabulated or they can be found in tables in the course of practice. All right, so in this case, in the BS, so let's say, since we're using the BS, so this is going to be in the BS 8110. I'll pull them up as we go along and then we'll see what these tables look like. Okay. The next note is that when you calculate the areas of reinforcement, we need to understand that because we have bending in two directions, it means that we'll have two different moment components for at least so in the two directions. Or even at midspan, we have two directions. Over support, we also have two directions. All right. So the areas of reinforcement we calculate to resist the moment needs to be done independently for each direction. All right. Let me put that into writing. To resist moments are determined um, independently. All right. Independently. Let me just make sure that the words are rightly and nicely written. So independently for each direction of the span. Okay. And then a few others, let me put them here too. Um, and the reinforcement ought to be, that's why it becomes a bit confusing, but again, that could be worked out. Reinforcements how to be or are in the directions parallel to the spans, okay? So for example, if you are looking at the shorter spans and you find your moment in that shorter span, when you calculate your area of reinforcement AS, and then we want to draw how they'll be placed in the slab, their direction pretty much have to be parallel to that span that we calculated for. All right. And then the reinforcement, which is this is very important. So reinforcement, what's happening to my pen? So reinforcement for the shorter span. So that's the LX in this case for the shorter span. Um, should be placed furthest from the neutral axis. Am I correct with my spelling? If it's wrong, furthest from the neutral axis. Okay, so this is also very important. What do I mean by that? Okay, if for example we take a slab, you have two reinforcements at the bottom. So there'll be one, or they'll be going at 90 degrees to each other. Now we are saying that the rebar here, the one furthest away from the neutral axis, basically is the one, is a rebar for the shorter span. Okay. And this will affect, so this affects the D value. So this affects the effective depth. Bracket D, which we have come across several times. All right. Then the last bit, the last note would be that when calculating span to effective depth ratio, this should be based on the shorter span, right? So the span to effective depth ratio are based on the shorter span. Okay. So these are the key notes which are critical to whatever we are doing. Once we understand this, it's easier to do all our calculations. You can calculate moments, and calculating moments can be done using coefficients which are in table forms, and always understand how the rebar arrangement is going to be done, and also what your effective depth will be. And also, if you are calculating the span to effective depth ratio, you know which of the spans to look at out for. Okay. So now let's see how to design, so slab design. Or simply supported slab spanning in two directions. Okay. That's a very long whatever, but the key thing is that the key words are two directions and then simply supported slab. All right, those are what is key to us. Okay. So if we have if we have so we have explained this whole support conditions, all right? So we would have, so there'll be bending in this direction. So the slab's going to bend in that direction. And also there'll also be bending in this direction. Okay. So there'll be bending in the two directions. Let me think it's best to use different colors to represent them. Okay, so this is one, and then this is the other bending. All right. So this is your Ly, and here is our Lx. All right. So bending in the Y direction, we call that bending. So we call this one MSY, and we call this one MXX. So I would explain what these are. Oops. So here, don't do that. Okay, great. So here our MXS is supposed to be the maximum, what's the name? Design, let me just add all of that. Design ultimate um, bending, right? Or moment. Design ultimate bending moment. Let me say moments. All right. In the what's the name? And there was a name. In the direction of span LX. Then our MXY, it's the same thing, just that this is going to be in the direction of what? Direction of oops, let me take this one up a little. It's this one green. Okay, so at least there's difference between the two. So this is in direction of LY. Okay, this is our MXY and MX. All right. And please, all of these are mid-span moments. So take a note, these for now. So let me just make sure I have you over here nicely. Okay, so these are mid-span moments. Okay, because we are assuming that the supports have pinned, so no moment at the supports. Okay. So the equation for finding so MSX or N subscript SX. So the M stands for moment, then the S is for span, and then the X here is for the direction of that span, right? So MSX is equal to alpha SX times N LX squared. Okay. Then MSY is equal to alpha SY and then NLX squared. All right. And then I'll explain what these terms are. Um, Let me explain what these terms are. So at least the LX squared, and I mean the LX is the length in the shorter span. At least that much we know. So what we need to, and there goes the screen again. Hopefully, okay. I'm hoping it comes back on without any stress. Great. Okay. So let's look at some of these parameters. So alpha, so this ones are very important. Let me put some thing around this. At least we know how important these things are. All right, great. So alpha XX, alpha SY, they are what you call coefficients. So these are the coefficients for simply supported slabs spanning in two directions. Okay. Uh, Then here, the N here stands for the total ultimate load. Okay. And this is usually per unit area. All right. So per meter square. Okay. So take note of that. And we already know what the L squared is, right? So, sorry, the LX is shorter span. So shorter span length. What else do I have to show? Um, okay. So if I want to like represent the moment, um, as it's supposed to look like, how do I even draw this here? Okay, let me just take this out of this place and bring it down. Bring it down here. So this is my uh, okay. So let me take this ones off for now and then just draw. So assuming I have a straight line in here, this is how my moment will look like. Okay. So this is for one, and this will basically be the moment in the X or the MSX, sorry. So this is my MSX. All right. As we have shown, so that's the bending. Then if you take here, this is my bending in this direction. Okay. So then this will be the MXY. All right. So if you take a look, you can see that the bending is highest around the span, and then it's zero at the supports. Okay. So let's look at an example, and then maybe that'll explain how this concept works. Okay. The other equation for n, which we already know, I mean, is 1.4 GK plus 1.6 QK. Okay, so that's supposed to be the live and then the dead load, right? And then once we calculate the moments MSX and MSY, we need to use this moment to find the area of steel, all right? So what this means is that I think I can move this one. Oops. I can move this towards the maybe further away because it's not too critical. So I mean I have to find the area of steel in the X direction, which will be ASX, and that will be MSX over 0.87 FYZ. All right. Then our AXY will be MSY, sorry, over 0.87 FYZ. All right. So again, these are equations that we have come across already. All right. But just rewriting them to suit what we are doing. All right. So let's look at a table. So I'm going to bring the table up and then we can use that to do our calculations. Yeah, so here we have the table from BS 8110. All right. Which shows the coefficients for a simply supported slab spanning in two directions. All right. So depending on the ratio of Ly over Lx, we can easily determine what our ratios would be. So let's try an example and then we can use that to explain a few things, okay? So let's look at example. So the example says that, let's see, we have a slab. Okay, let me just, oops, this looks terrible. Okay, let me just put that to writing and then we can look at it. So design, what's the name? The reinforcements. Okay. Uh, for a simply supported slab. All right. Which is 220 millimeters thick and spanning in two directions. Okay. So the sorry. Let's look at it. We have let's say so this are our span. Let's put together some information that we'll need. Okay, so this is the panel. Here is 4.5 meters. This is 6.3 meters. And then the live load, QK, which is a live load, just put into brackets, has given us 10 kilonewtons per meter squared. And then the GK, which is the dead load, sorry. Oh, okay, I think I have the load over here. Okay, we'll look for the load shortly. Then our FY, which is the strength of the steel, the yield strength is 460. So this is supposed to be a high strength, high yield strength. And then the concrete is 30 newtons per millimeter squared. All right. So with the dead load, we've not been given the actual dead, like any additional dead load, maybe let's say partitions or whatever. But then we know that the what's the name? The the weight of the material would also be considered as dead load. All right. So let's find out how to convert the weight of the slab from its weight and then convert that into a load. Okay. So I'll do that on the side and just so that we know how it's done. So let's just start with a solution. Okay. So the first thing we need to do is to figure out if this our slab is a two-way or a one-way slab. All right. So we start with Ly over Lx, so the longer span over the shorter span. So 6.3 over 4.5, and this should give us 1.4. Okay. So since this is less than 2, this means it's a two-way or two directions, right? Two-way spanning. TWO, yeah, two-way spanning slab. Okay. And this is simply supported. So there's nothing else to add to it. Now let's find the N or the load, right? We know that we have to find, basically we have to find MSX and then find MSY, all right? And then we know our MSX is equal to uh, alpha SX and LX squared. Then our MSY is alpha XY and LX squared, sorry, not LY squared, LX squared. So what do? Um, let's find n. All right. So let's find n, which is supposed to be our ultimate load. To bracket ultimate design load. So let's find the self weight. So the self weight basically is equal to the thickness of slab times the unit weight of concrete, okay, of RC concrete. Okay. And normally the unit weight of concrete uh, using the BS code is giving us 24 kilonewtons per um, meters cube. All right, so 24 kilograms per meter cube. Okay, so we need to, the thickness was given to us as 220 from the question was given to us as 220 millimeters. So let's convert that into meters. It becomes 220 over 1,000. Okay, that'll be to convert to millimeters times 24. And this will give us 5.3 kilonewtons per meter squared. All right. So here N will be 1.4 GK plus 1.6 QK. And this is 1.4 times 5.3 plus 1.6 times, I think we had 10 for the live load. And this should give us 23.4 kilonewtons per meter squared. So now we have our N. Let's find our alphas, the alpha SX and then the alpha SY. Okay. So let me just bring the table. I'm going to bring the table down again. I have it here. So just make a copy of it. Copy. Okay. I'll hopefully copy it. Let's paste it down here and see. Yeah, it did copy. Great. So you have the table over here. Okay. Our ratio is 1.4. So this is our LX over LY ratio. So this is 1.4, which means that my alpha SX is 0 0.09, sorry. So 0.099. And then the alpha XY is 0.051. Okay. So take note where Alex, or I mean, let me just say that right here. Sometimes you need to do interpolation, all right? Do interpolation where you cannot find the exact value of Ly, Lx on this table. You have to interpolate that. And then we've gone through how to do these interpolations for tables of these sorts. Okay. So once we have that, we can find our MSX, and MXY. So here, my MSX will be equal to alpha SX, which is 0.99, 0.099 times an N of 23.4 kilonewtons per meter squared, then times an LX of 4.5 squared meters. The LX is the shorter length or the shorter span. Okay. So if you do these calculations, you will end up with 26.9 kilonewton meter. Okay. Will that be your MSX? So let's say, let me put a small side note over here. Let's say we're looking for bending in the shorter span. Okay. Or let's say bending to bracket short span. I don't have to go through all of that. Okay. So once we find our MSX, we can use that to find our K. All right. K is equal to MSX over BD squared FCU or F sub CU. And this is 46.9 times 10 exponent 6 divided by the B is 1,000. All right. For a slab, your B is always 1,000 millimeters. So 1,000 times a D. Um, I don't think we did any D calculations, but we can assume some D values. All right. I'm going to do this on the side so that at least we always have that in mind. Maybe I can do that over here. It's fine. Okay. The height of the slab is 220 millimeters. All right. So we can assume that our D can be around 185 millimeters. How do we come about the D? All right. If we know the clear cover, so let's say if the cover was given as maybe, let's say 25 millimeters cover. All right. Um, so let me just do the math for you. 220 minus 25. And let's say maybe we assume our bar diameter to be, let's say, 20 millimeters. All right. It's usually less than that. So that means that the D will be equal to H minus C minus phi over 2. Right. Yep. Okay. So then this will give us so this might give us let's say maybe 220 minus 25 minus 10 over 2. That's approximately some value, right? Maybe 1. Am I correct? No, so 20 over 2, not 10. 20 over 2. So that should give us roughly about 185. All right. It's just an assumption. All right. That we are working with. Okay, so this sorry, this should make some sense as to how to get a D, right? And then as part of our notes, we mentioned that when choosing the D, you have to take into consideration a short span, right? Okay. So then this would give us 185 times an FC of 30, and that should give us 0.046. All right. Okay. And those very small values indicates that when calculating for AS, where ASX is equal to MSX over 0.87 F sub YZ, the Z is usually 0.95 D for very small values of this sort. Okay. So it means that our Z here will be 0.95 times 185, which then would give us 175 millimeters. Okay. So here ASX will be equal to 46.9 times 10 exponent 3, 10 exponent 6 divided by 0.87 times an FY of 460 times a Z of 176. So ASX would give us 66 millimeter squared per meter length. All right. Again, I think I mentioned this in the last lecture that we are looking at per meter width of the slab. So everything is calculated per that meter width. All right. So let's say, so let's say our diameter of bars is 12 millimeters. All right. So that means that um, the table, I think from the previous lecture, we had a table that was useful to us. Let me just bring it up. Excuse me. So there's a table that, I mean, the area table for slabs, right? That's slightly different from the area table for um, beams. Okay. So where, yeah, let me just pull that from the previous lecture. If I can find it, that'll be great. Okay, so I have seen it. Um, okay, so yeah, it's showing right here. So based on that table, we can calculate or find the area. So let's say we got 666 to be our area of steel required. I could come into this table, assuming I'm using a spacing of, let's say, 150 millimeters for the bars. So I could go with, so T12, so that's going to be this zone right here. So in this case, we will choose 7574. All right. So I could write that provide T12 at 150 millimeters centers. All right. So that our area of steel provided will be 754 millimeter squared per meter. So this will be the bending in the short span. All right. We can check the span to effective depth ratio, and then just to make sure that everything is correct. All right. So let's just check that on the side. So let's see. Let's check the span effective ratio, depth ratio. Sorry. So we can find our MSX over just BD squared, and that should give us I think 1.37. And then from there we can go into the table. Let me again, I prefer that we see the tables as they are in real time so that we appreciate what is going on with our computations. So let me just bring the table up again. The table to determine the, what's the name? The 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 stresses. So I think that'll be table 3.10, 3.10 in the BS code. So let me pull that down. Let's see. So once you have this table, since our FY is 460. All right, so we have this. We got 1.37. So that is somewhere here. I believe this is where our 1.37 lies, which means that our value would be somewhere in between these two, okay, which we can use interpolation to determine. All right, so this is normal. This will be 1.25 from the table. So based on that, um, a limiting span over effective depth. So should be 20 times 1.25. All right, that 20 is gotten from the fact that we are looking at a simply supported slab. All right, so there's the basic ratio for what the span to effective depth would be. All right. So that's 20. So this will give us 25.0. Now let's compare that to the actual span to effective depth that we chose. So our span was 4.5, which is 4,500 millimeters over 185. And this will be equal to 24.3. All right. So since 24.3 is less than 25, then D is adequate. So here, D of 185 millimeters is adequate. Okay. That's great. All right. Now let's look at the bending in the long span. Okay, so this may be bending in the long span. So you will see that everything, like the same process, we find MXY, we find AXY, and then all of that. So very straightforward. So our MXY will be alpha X SY and LX squared. Please take note, it is LS squared for both cases. So alpha SY was 0.051. Okay. So 0.051 times the n of 23.4 times 4.5 squared. And this will give us 24.2 kilonewton meter. Okay. And normally, or usually, we will see that the moment for the long span is usually less as compared to the moment for the short span. All right. So once we have that, we need to find D. All right. Normally the D for the long span is less than the D for the short span. Let's take note of that as well. So we know that our ASY will be equal to MXY over 0.87 FYZ. All right. So our previous Z that we had for the short span, okay, Z for the short span, I think was 176 millimeters. Okay. So if we want to find a Z for the long span, it will be that 176 minus the thickness of the rebar or the diameter of the rebar, sorry, which is 12 millimeters. Okay, so that'll give us 160, am I correct? 164, yeah, millimeters. Okay, you can also use D to calculate it, doesn't change anything. So that means that our ASY will be 24.2 times 10 exponent 6 divided by 0.87 times 460 times 164, and this will give us 369 millimeters squared per meter. Okay. So again, let me put this into table. Always check minimum. Always check AS minimum, please. Very important. Always check. When you're doing design, we always check. We check if our AS minimum or if the area of steel we are getting from our calculations is less than the minimum required. So if it is less than the minimum required, we go with the minimum. If it's more than the minimum, then we are good. Okay, so let's take note of that. as well. So again, we come to the table, the cross-sectional area table. If let's say we are using 200 centers, it means that we would, let's say also in this case, we are going with T10. So T10 for 200 centers, our focus will be on this value 393 millimeters squared per meter. So provide T10 at 200 millimeters centers. Okay. So that our area of steel provided will be 393 millimeter squared per meter. All right. So let's see how we can put that into drawing. Okay. And then just see how the rebars will be arranged. Okay. So let me have a platform for that. Okay, shapes. No, not here. Why are you drawing over there? Wrong. Wow, this is strange. Okay. So let's try and redraw the shape. Hopefully it works this time around. Okay, great. So let's say this is so this is our slab in the shorter span direction. So let's say we have the beams as supports at these ends. All right. So our effective length or span length here will be 4.5 meters. Okay. 4.5 meters. Okay. So my rebar, let me just exaggerate the thickness. So here, I would have, let me see if I can draw a nice line here to indicate my rebar rate. So I have my rebar here, and I have some other rebar. I have rebars in this space. One, maybe a few, just to illustrate what is happening. Okay, great. Okay, so the purple here is the T12 at 150. Okay, so that's supposed to be parallel to the shorter span. Then this one here is our T10 at 200, which is for the longer span. Okay. And that is basically how we deal with it. So this is like the elevation view. If you want to draw the plan view, this is how the plan view would look like for the same. This is how did I draw my earlier? Okay, so this is wrong. So this one looks more like it. Let me just increase the size a little, just a little bit. Yes. Okay, great. All right. So assuming that this is the panel in plan, of course, this end here is our 4.5. So let me draw that bar again. So this is how we do it. So we have a bar, all right. And this bar, I'm gonna change this color. Let me make it, maybe make it green, it's fine. Hmm. So we have this bar, and this is, okay. So in plan, this is, the bar goes in this direction, upwards and down, I mean, up, like, goes in that direction. And so sometimes what we do is that we actually extend this horizontal, this line, this vertical line. In this case, we extend a little bit. Okay. So you'll see that it has this little red marker, sorry, to indicate where it ends. And then you see that maybe we write here, let's say T12 at 150. So T12 at 150. So this is how we usually write it. Again, depending on your design office, things might be slightly different, but the idea is the same, or the processes involved is the same. All right. The other option to be, now we also have this bar, and let me increase the thickness of it. Okay. So we can have this bar here, and then we do another line, maybe just somewhere here. Okay. Now this color is the bar color. So let's go with the red, it's fine. So this is where they intersect. Okay, so this is so basically it's a rebar and then the indicator lines, all right? The red here is the indicator line, and the pink is supposed to be the rebar. So this is where the bar ends. Okay. Then maybe, so this becomes T10 at 200 millimeters, all right? If you want to know the number of bars that we have, again, just divide the bars, I mean the spacing. So the spacing is 200, and then you know the length, how many we want. So for example, if you want to know the number of rebars, in this case, all right, the entire length, so this is for long, let me write here, this is for the long span, this is for the long span, okay? And this is for the short span. Okay. So if we know the number of rebars that we need, you can easily do a simple calculation. You know the length is going to span. So for the long span rebars, they will span on the short side. All right. So it's 4,500 divided by a spacing of 200. All right. Typically plus one. So that will be what's the word? 4,500 divided by 200 plus one will give us roughly 23.5. So that will be about 24. Okay. So I can actually come here and write that, okay, this is 24, maybe 24 T10 at 200 millimeter centers. Okay. Then for this guy also, or for the short span, the number of rebars will be 6,300 divided by 150 plus 1, and that should give me, so that's going to be a lot compared to the other one. So that would be 43. All right. So here I could also come in here and write that 43 T T12. All right. Okay. If you want to, again, we can label it a bit further to complete it. I'm running out of space for this guy here. So let me just clean it first and then go back and then maybe drop this a little bit more. Okay, great. So to indicate which one is the most bottom, so I have here 43 T10 at 150. This is B1, the bottommost one, and here will be your B2. So basically, this is how we do the rebar arrangement for slabs. All right. We'll look at curtailment and then all of that shortly. I mean, we'll spend a bit of time to look at rebar, curtailment, and then all of that as we go along. But in its simple terms, this is how we do. Oops, yeah. So in its simple terms, this is how we do the rebar. So this is I think so. This is all there is to do with respect to slabs. But again, one of the things we need to check, it has to do with shear, right? Check shear. But normally we try to design these types of conventional solid slabs to not have any need for shear reinforcement. Not always, sometimes we need to. So it is on you as the designer to ensure that you always are checking for some of these things. All right.